Let's go through some of the questions from the Chapter 10 review, starting with problem number 4. Find the area of the shaded segment of the circle. Again, we're going to go through more of a process than a formula here. We're going to find the area of the large sector, subtract the area of that central triangle, and the difference will be the segment of the circle. Okay, so to find this area, we're going to start with the area of a sector. If they gave us this 120-degree arc measure, that means the central angle here is also 120 degrees. So 120 always divided by 360. And again, we're dealing with area, so we want area of the entire circle. Pi times, they gave us the radius there of 6 centimeters squared. So let's go ahead and take care of this first, and then we'll deal with the triangle because there's significantly more involved. 120 over 360, that's 1/3. 6 squared is 36. 1/3 of 36 should give us 12 pi. Now, let's talk about our lovely central triangle here. Again, it's isosceles because two of the sides are made up of radii of the circle. They have to be congruent. So that means our central angle is the vertex angle for the triangle. And if we want to go with 1/2 base times height, yeah, at this point in time, we don't know either of those. So let's put in an altitude to the base of the triangle. Now again, an altitude should make that a 90-degree angle, and it should be an angle bisector. So this 120-degree central angle now becomes 60 on this side, 60 on the other side. Lo and behold, we have our old friend, the 30, 60, 90 triangle. The 6 centimeter side in our 30, 60, 90 right triangle is the hypotenuse, which means then the shorter leg opposite, it's a small picture. I'm not going to label the 30, but hopefully you can tell where that is. Half the length of the hypotenuse, so that has to be 3. And then the longer leg is 3 square root of 3. Well, everything that's true for this 30, 60, 90 here on the lower right portion is true for the 30, 60, 90 here in the upper left. So this is 6. This is 3 square root of 3. So we can say our entire base now is 6 square root of 3. The height of the triangle is 3. We've got everything we need. 1/2 times base times height. Half of 6 square root of 3 would be 3 square root of 3 times 3. That'll give us 9 square root of 3. And they asked you for the area rounded to the nearest tenth as needed. Oh, we are definitely going to needed here. So you can just type that in exactly as you see. 12 pi minus 9 square root of 3. That'll give us 22.110654, blah, blah, blah. But again, if it says round to the nearest tenth, we chop that off at about 22.1. Number 5, find the radius of a circle whose central angle alpha intercepts an arc of the given length, S. Well, okay, so now our formula here for arc length is just going to be, again, arc measure. So that's 36 degrees, always divided by 360. But now times the circumference of the circle, 2 pi r. Well, again, we're trying to find the radius, so we can substitute in place of the arc length 22. So, yeah, in whatever order makes the most sense to you, one of the things that jumps out to me here is that 2 divide both sides. So that becomes 11. 36 over 360 is 1/10. So now I can get rid of that fraction by multiplying both sides by 10. So one more step here. Divide both sides by pi. That should tell me what my radius is approximately. Round to the nearest hundredth as needed. Oh yes, we do need. So 110 divided by pi. Force the decimal approximation to the nearest tenth. I guess we round that off to 35.0. Oh, I'm sorry, hundredth. 35.014 becomes 35.01. And again, that's meters. We're looking for the length of the radius. It's not square meters. It's a measurement of distance. Number 6. Oh my goodness, look at all the different parts they wanted here. Well, if we can figure out some basics, this isn't really all that tough. Athletic field is 46 yards by 92 yards. It has semicircles at each of the short sides. Now here's a key thing. The track is 10 yards wide. Okay, so the track is divided into 8 lanes of equal width. Lane 1 being the innermost, lane 8 of course being the outermost. What's the distance around the track along the inside edge of each lane? All right, so again, looking at this semicircle here, this 46 yards, that turns out to be the diameter of the semicircle. So for lane 1, we have a radius of 23 yards. Now, mind you, if we follow the path of that semicircle going around here, and if you're going to run a full lap, you're going to run a semicircle there. That gives you the entire circumference of a full circle. Okay, so this total distance here, we're going to run the straightaway of 92 yards twice, and then we're going to run the circumference of an entire circle, 2 pi times 23. Type an integer or a decimal rounded to 2 decimal places as needed. So again, you really don't have to do too much of that. I'll let the calculator, if we're going to round it off anyway, 328.51. I believe that matches up. All right, so now it comes to what do we do for lane number 2? Now again, the track is 10 yards wide, so from that center point to the inner edge, we know that that's 23. To the outer edge, that's got to be 33. That 10-yard distance, though, is split up among 8 lanes. So we take that 10-yard distance divided evenly among the 8 lanes. That means each lane has to be 1.25 yards. Was in yards, yes, yards wide. So that means we're just going to add 1.25 yards to the radius. So 23 plus the 1.25 should give us the 24.25. And now we're going to keep everything else the same. We're just going to bit by bit by bit change each radius. Okay, So for lane 2, it'll be 24.25. So that'll give us 336.37, I guess, if we're going to 2 decimal places here. For lane 3, we're going to add another 1.25, so the radius there will be 25.5, etc., all the way on out there to lane 8. Okay. And then finally, number 12, circle over here represents a planet. The radius of the planet is about 5,300 kilometers. Find the distance d, this little segment here, to the horizon that a person can see on a clear day from the following height h on the planet. So if somehow the person is 6 kilometers above the surface of the planet, how far out can he see? All right, well, we're told here that this radius is, please note, it's not drawn to scale. Why did they put that? This radius has a length the hypotenuse of the right triangle is the radius of the planet plus that person being 6 kilometers higher. Our hypotenuse, a squared plus b squared equals c squared, is 5,306. And we know that a line tangent to the circle has to be perpendicular to the point of tangency at that lovely radius there. So we can use our Pythagorean theorem. The distance squared plus the 5,300 squared has to be equal to 5,306 squared. All right, those are not quite exactly numbers I expect you to know off the top of your head. So if we do the algebra here and subtract the 5,300 squared from both sides, again, type it in your calculator will take care of order of operation and square those values and then take the difference between them, and it's a whopping, oh my goodness, look at how far, no, hold on, that's still the square of the distance. So now we need to take the square root of our previous value there, and this gives us our actual answer there of about 252 point nearest tenth, 252.3 kilometers. Just getting 6 kilometers above the surface of that particular planet allows a person to see more than 250 kilometers. Just for reference, the radius of this planet is about 5,300 kilometers. Ours is bigger. All right, so that's pretty much it. Those were the only questions I was sent. Hopefully that clears up a few things. Tangents perpendicular to the radius at the point of tangency. Make sure that you do know the formula there, area and circumference. You should have known that before. Arc length is a fraction of circumference. Area of a sector is a fraction of the area of the full circle. And of course, our process there for finding area of a segment of a circle.